Hello everyone. So I'm Sebastian Hilaire, yes, rendering engineer at Frostbite. And I'm here to talk about real-time raytracing for interactive global illumination workflows in Frostbite. In this talk, first I will talk a bit about the context and the current workflows we have. And then I will describe how we implemented the GI live preview technology in Frostbite using DirectX 12, DXR, APIs, and first on NVIDIA RTX technology. So a bit of context, Frostbite is the EA game engine, the one engine that empowers all those games you see here. And as you can see, there's a lot of different kind of games. Global illumination in these games has historically been evaluated using Enlighten, which is a very advanced system. It supports dynamic GI update, so you can run a dynamic time of day, moving light, and it supports also destruction. And on the side of that, we also can resolve global illumination data using Flux, which is our custom path tracer. And this is targeted to when we want fully pre-computed lighting, with a focus on high density, high quality, and performance. And this is used, for example, in Madden, FIFA, or Battlefront, or Star Wars Battlefront 2. So Flux is a path tracer, as I said. CPU baking of the global illumination data is achieved using Intel Ambry for the ray tracing side, and Incredible to distribute the workload on different stations. If you want to know more about Flux and all the details about it, and a lot of details about how you pack the light maps and the charts in the light maps and specular light maps, you should definitely check out Yuri's talk tomorrow. It's a very, very great talk. And so a few results about Flux. You can see here Heinz Field Stadium from Pittsburgh in Madden. On the left, you have direct light and indirect light baked, visualized on the stadium. And on the right, you have the final result in game. Here is the screenshot from FIFA of the Etihad Stadium. And you can see again on the left, only GI bound in this case, and then the result in game at dusk time. A few more about Star Wars Battlefront 2. Here we visualize a light map on proxy meshes that we use when we retrace the scene to generate the light maps. This is the same scene, but with the final meshes used in-game with normal map applied. And here you can see with the sun, the direct light from the sun, which is the main contributor to global illumination in this scene. And as the final result, with everything applied as you can see it in-game in the end. So what about the workflow? What does artists have to do to obtain those results? First, they have to open our editor called Trusted. And if it's a new level, they have to start from scratch. Otherwise, they will have the previous GI visible in here. Then they have to author the scene, move the light, move meshes, do what they want to achieve, basically. And then they should start a baking process, which can take between from a few minutes to hours, of course, depending on the quality you want. Then you check the result. Okay, that's how it is. Maybe that's how it is. That's what you wanted to achieve. Awesome, great. Next task, or you can have a coffee. And if not, well, rinse and repeat. You go back to the start and iterate. So, of course, we did try CPU GI preview with what Flux was providing at the time, but that was too slow for our constraint. So if you step back and think about the problem, what you want to do is evaluate irradiance. If you consider light maps, what you want to do is evaluate irradiance for each texel, and for that you can use path tracing. And you have to, using path tracing, you have to integrate irradiance over the hemisphere. And that is, if you think about it, that's a massively parallel problem. Each light map texel is independent. Each path for each texel is independent. So that sounds like a perfect fit for GPUs, of course. And then, of course, one array is not enough. You have to integrate multiple of them, and that can be done using Monte Carlo integration. And of course, the more array you cast, the better you will converge toward the real solution of the irradiance for each texel. And so that seems like a good solution for preview. You start with a rough estimate, and then you converge progressively toward the right solution. Yeah. So that's what we then aimed to do. Basically, a Flux as a functional prototype working like running on GPU using the DXR API, and first on NVIDIA RTX technology because they gave us access to early drivers for GI preview. I will not give any details about the DXR API and how it's used in this presentation. You should refer to the Microsoft presentation from this morning, but I will describe the technique we use. So this is an example of an artist playing in the scene, moving the light. Then you can see the light map automatically refreshing. You have some dynamic objects also in the scene that are picking up light probes. You can change light maps, emissive materials on the hand here, and you can move meshes, and you can see if you remove the ceiling, you can see the light pouring in from the sun. So that's an example of authoring. You can see also colored bounce light at the back from the red cloth. Okay. So what do we need to provide as input to be able to achieve that? So of course you need your input meshes, triangles, lightmap UVs. You also need materials. For that, per triangles, we have albedo, translucency, emissive irradiance. And of course, we take into account every light type that Frostbite supports, and the sky also. So what does Flux output? First, there's a set of light maps storing irradiance for each texel, and also a dominant light incoming direction that can be used, for example, to achieve normal mapping. And also on the side, we also have irradiance volume, storing irradiance in each of the voxel of volumes as spherical harmonics L2. You have visualization of those on the right here. And what's important to understand at this stage is that the algorithm we use to preview is the same as the one we will use when we will bake everything on GPU. It will be the same algorithm, just a progressive view of it. The only thing we give is we give artists a way to accelerate the preview with some techniques I'm going to describe. And so once you have all that assembled, you can preview, of course. You can preview your scene. And in this case, you can see a light lighting the ground, all the object being affected by the bounce light around, and even the participating media scatters the light using irradiance volume. Another video, so you have a spotlight here without global illumination. Now with global illumination affecting all the objects in the scene, adding more light, enabling again global illumination on those lights. And you can also use a bright spotlight just to show you the effect of the albedo. Depending on where you point the spotlight, then the global illumination data will automatically update. It's quite fast. Of course, it depends on the level, but you can see it like converge quite quickly. Another example, in this case, as I said, we can change material. So in this case, the tube at the top, we are switching them from being metal to emissive, bright, so they act like neons. And that automatically affects the scene. You get automatic lighting from those neons, and it can be any shapes, of course. So what's the setup to be able to run this preview? Of course, you can use a single GPU, but Frostbite and Flux will compete for it. And even if you try to adapt your budget to fit a certain frame rate, you will never get something very nice. The best is, of course, 2 GPU. One with Frostbite running on one GPU and Flux running on the side GPU. That's like a perfect use case. And we run in asynchronous mode, so the two different processes can run as fast as they can. For example, Frostbite, as I said, on the first GPU, and Flux on the second. And we just copy over the data once it's available asynchronously. Right. So what do we need to do to evaluate irradiance for a texel of a light map that you can see on the left here? So we use, of course, DXR to cast a ray, intersect with the geometry, find a first vertex on the path, and from there we do next event estimation. So you cast a secondary ray, shadow ray, we call it, toward the light source. If it's not occluded, then you can accumulate, and then go toward the next event, the next intersection, by casting another ray with a random selection, typical path tracing. Then for that new vertex on the path, it's the same. You can cast another ray to test visibility. And if it's not visible, you will not accumulate that light source. We do that for all the light source, and we have an acceleration structure, but I will not describe it in this talk, because it's not important for this talk. And so on and so on. We continue for n vertex on the path, and if then in the end we fall out, we don't intersect anything, we can sample the sky environment map, for instance. We accumulate over time all those, as I said, using Monte Carlo integration, we accumulate over time all those samples. And when the artists move a mesh, update a material, or whatever, anything changes, we then reset the process. Because then everything is invalid, can be invalid. And then we notice that shadow rays can be expensive, mostly because they kind of are incoherent. They can go in a lot of different directions depending on its surface. So to solve or to accelerate the process, we then use a naive irradiance cache for the direct light component, which is sun, local light, and emissive. And this is the cache match exactly the light map. As of today, we could make it higher resolution. Why not? But that's how it is. And so each frame, how does it work? Each frame, we just evaluate all the light sources according to some shadow rays. We accumulate all the contribution in the texels. And we do that over multiple frames also because we want to integrate area light, for instance, or emissive surfaces. And once that is done, then sampling the next, doing a next event estimation, it's just a texture fetch on the path. You don't need to cast secondary ray. That accelerates everything. And it's also convenient because for translucency, for instance, once you have integrated all your irradiance, well, you can just sample that from your irradiance cache and affect that value by the albedo. And that will automatically affect the light. So you can have translucent surface the same way. It doesn't have to cast more ray from front and behind. An example in that video, you can see we move a translucent mesh affecting the full world. You can see the light map completely always restarting when we move the mesh, and then it like converges. So of course, we need to also not evaluate all the texel of a light map. If you have multiple light maps in your level, you can have super high resolution light map. You do not want to evaluate all the texels, that will be too expensive. So what we do is we prioritize as a function of where you look at. So to this aim, we just render cast rays from the camera, according to one ray per tile. We have some tiles. And each time we intersect a surface, we append that, we schedule that texel to be updated. And this is quite fast, like we can schedule 1.3 million paths with only 7.15 milliseconds. And the video on the right shows like the update at the rate, how we select texels according to this camera path here. And it's like slowed down by a lot just to demonstrate the updates happening. But otherwise, you do not see it really. So noise, of course. If you know, well, like Flux is just a forward path tracer, so it's subject to noise due to complex scene, complex path, complex light sources. Can be anything. So we try to fix that, and the attempt is, what we do first is we track the running variance per texel of the light map we are evaluating. And that is used for different things, to balance the budget first, because if we know that a texel has converged, then we don't need to schedule it. We know that, okay, it has converged, let's skip it. It's for preview, so it's okay. And we use it also to denoise the light map. And to this aim, we use the R-true filter, the same R-true filter that's used for SVGF. And you can see on the right, at the top, unfiltered light map, so noisy. And at the bottom, the filtered light map using the SVGF filter. And the small image at the middle is showing the variance. Red has super high variance, and blue has converged. And this is applied on the light map each frame, and before it's presented in the editor, basically. And that's a video showing it in action. So at the top, you can see the variance. Some texels are converging more faster than others. You can see, you look at the indirect shadow from the column here. At the beginning, it's very blurry, but progressively, it just becomes sharper and sharper and sharper. Maybe I can try to show. No, I can't. Okay. So, and the goal of this blurring process, of course, is first to avoid the annoying noise that happens when an artist is updating the scene, and also, of course, for quality. So in the future, one additional thing we would like to do is to try to mix image space and light map space denoiser. And on top of that, also is to have an indirect irradiance cache, because then we can shorten the path. Like if we know that the indirect light has converged, we can also stop the path we are tracing right now, because we know that if we continue, it will not add any information, any additional valuable information. So as I said, we output light maps. I just described how we evaluate it. And now we also output irradiance volumes. And it's the same as the, all the code is the same. It's just the way we launch ray. Instead of launching rays over an hemisphere, we launch the rays over a sphere, starting from each probe position. And we just saw that as spherical harmonic L2. A bunch of numbers now, performance. You can see the different performance results we have for different levels, different setup, different amount of local light. For example, you can see sci-fi by default 70 million rays per second. And if you use the irradiance cache, which helps when you have many light, then you can go up to 300 million rays per second. A bunch of future thoughts. Of course, path tracing can be improved. Like we just have a basic version with a basic irradiance cache. All the research that has been conducted in that area could probably be applied and tried at least. Bidirectional path tracing, path guiding, maybe a better irradiance cache representation. We also want to try 1 plus n GPU. So you could have n GPU running n Flux instances, and you could combine all those light maps at the end, and each GPU will have different noise random seed to make sure it can all be combined correctly. And last but not the least, GPU farm. We don't want necessarily all artists to have like 15 cards in the setup, so it would be good to have a GPU farm that could provide as a service the sampling on all of the preview of all those light maps, and of course for baking the game when it needs to ship. Then we'll need a GPU farm to make sure it's super fast instead of hours, maybe just less than an hour of baking time. So that's it. That's how we implemented, that's what we have to preview interactive global illumination in Frostbite. The benefits, definitely faster iterations. Like definitely now artists can play around and move stuff around. It's just a matter of seconds. So productivity will go up, we expect. But not only productivity, but quality. Artists will maybe try to play more with more lights or different material albedo, try to experiment a bit more because the result is almost instant. And there's a funny story, not funny, but funny anecdote is like at the beginning we were telling artists, okay, what do you think if we give you interactive preview of GI? Like, oh, okay, maybe that's interesting. But then they saw it, like, and that something clicks, like something happened, and they're very interested in having that all the time now. So maybe we can say that Raytracing is back from the future, maybe. So thanks to the full team at Frostbite, because I'm just presenting. Everyone has worked hard on that project here. And that's it. Oh, hey.
Yeah, one question.
Yep.
I actually did ray tracing research like 10 years ago. And there was, for example, Timo Ailain Terokara's ray tracer by NVIDIA Research on CUDA. It was actually pretty efficient. So I'm wondering, and I think it would have been possible to do real-time previews even back then. So why do you think now we're getting back to it? Only because there's DirectX ray tracing API. I mean, CUDA was pretty usable even back then.
Yeah, so that's a very good question. And I think you're correct. It was possible before, but I think now it's easier even. And maybe at the time that was not a big problem, or it was accepted. But now that it's like available easily and very efficient. I mean, I don't know what were the performance at the time, but now it's like very efficient as to what we have measured. So maybe like I don't know, like.
Yeah, it was basically 100 million rays per second.
Yeah.
If you can do it.
Yeah. So, yeah.
Oh yeah, I can start. So me and Colin, we're also from Electronic Arts, and we're going to talk a little bit about a demo we've been building that also uses real-time ray tracing and the new DXR API and NVIDIA's RTX implementation and running on some really cool hardware. So we're both from a group called SEED, Search for Extraordinary Experiences Division, which is essentially a research group at Electronic Arts, where we explore new creative and technical approaches and different technologies and trying to figure out what the future of interactive entertainment is, which is super easy. So part of this, we're exploring quite a few different type of technologies, anything from machine learning for doing agents, and we actually have a talk about that later tomorrow, to various procedural approaches of how to create environments, and part of this demo that I'm showing is procedurally built, so there's another talk about that tomorrow as well, and ray tracing that happen to align fairly well. So before saying too much, I'll just show you a video or a trailer of a small project that we've been building. Thanks. So this is a small mini game and world that we've been building for just the last few months. We got an early build of DXR, and we wanted to try, in general, actually within C, to combine a bunch of different technologies and different ideas that we've been having to build something small and concrete. So we came up with this small project, Pika Pika, which is a code name for it, which is essentially a small mini game, and that game is really created for our small self-learning AIs that run around in this environment, and essentially they repair the machines that keep breaking down here. So they're running some small neural networks to figure out how to traverse the environment and interact in it. So it's not a game built for humans, none of you guys. It's a game built for our agents, our future AI overlords. So this is actually using our small R&D engine, or sort of research framework that we're using in Seed, called Halcyon. And some of our goals for this was, well, obviously to explore ray tracing and the various types of hybrid techniques that we can do with that, with DXR and all the developments with that. But we also wanted to create something with really like clean and consistent and simple visuals, where artists were empowered to just create something cute, small, and nice, and where through the ray tracing and some of the stuff we have in Halcyon, we just make that come alive, essentially, and make it very consistent and just work. So there's no pre-computation in this. There's no like calculated light maps and some of that. We don't necessarily get the highest quality that you may have seen in the Frostbite talk, but we get the really clean and consistent visuals, and everything's dynamic. And a very important thing for us, our team is really quite small. We have 3 artists in total. So not having to have artists manually placing things like local reflection volumes in the scenes, or all this manual craft that you have to do to create high-quality AAA visuals nowadays. So ray tracing was very helpful for all that. And a couple of more components for it. So ray tracing for us is really just another tool in our toolbox, but it's a really, really flexible and pretty awesome tool, specifically to solve some really long-running problems and challenges we've been having with more sparse rendering or sort of incoherent problems, in things from things like reflections, especially on non-planar surfaces in that sense, or where you want to distribute, well, render only small portions in your scene in that. Rasterization is an awesome, very fast, well-optimized method for the last 20 years, and we'll continue to use it. But there's a lot of other approaches or a lot of challenges we haven't really been able to tackle with it, and I don't think we'll going forward either. Why ray tracing right now? Well, having this unified API where we were able to both do rasterization and do compute, as well as ray tracing, all combined into the same API that we've been using, which is DX12, is super helpful, and it makes it actually a really big difference for us. That combined with also having the performance of, well, the latest generation of GPUs with the NVIDIA's Volta, and with all of the work that they put into RTX to really have this ray tracing runtime. Sort of all of these things connect to make it a good opportunity for us right now. And we are able to get to really high quality visuals really quite easily without lots of artist work, and also have a very easy path to get to the ground truth visuals. How should it really look like if we have a high quality path tracer for it? So we have a reference path tracer for it, which is somewhat interactive. It's not for real-time visuals like this, but to at least see how everything works together. It's super useful. So I also mentioned that we have our self-learning AI agents. So I won't be talking that much about it, but I want, as we have another talk around it tomorrow, but I want to mention a little bit around it. So it's a technique that uses deep reinforcement learning, which is a machine learning technique, and we actually published a paper and another video and blog post last week about it called Imitation Learning with Concurrent Actions in 3D Games. It's up on Archive. Which is big deep learning community. So these agents, our goal with them is that we don't want to program AIs anymore. Well, at least we don't want to program every single thing in them. It's very time consuming, and we want them to figure out and learn new types of environments. So in this game, as I mentioned, the goal is to repair these machines that are breaking down. And in this, so we actually render out visuals, and we can do it in many different ways. And in this specific demo, we have this sort of fairly simple semantic view, which is not using ray tracing at this point. It's using rasterization, but we can render them extremely efficiently. And this is without optimizations that much either. But we can render very, very efficiently these fairly simple views that just give the agents a semantic view from their viewpoint. And feed that into a neural network architecture that we have, that we train in TensorFlow over, like, I think it takes half a day or something like that. And out comes a trained neural network that we run in this demo live with a couple of agents. So right now when we run it, it's a little bit, how do I say it? The goal for that sort of runtime inference is to use WinML, that also was recently announced by Microsoft, but right now we're using TensorFlow for the runtime also. And you may wonder what the small yellow things are on the sides there. That's actually us simulating hearing, or a bit of like a mini-map for the agents to know what are things around them. Because if you give them a first-person view, they can become kind of stupid if they get hit from the back or not really know how to navigate. But we're giving them a little bit of extra information in the scene, but this is all the information that they have. And it's kind of funny, you just write data into these pixels and the neural network figures out what to do with it. And of course, we have to shape some rewards and for how this gameplay, what's the goal of it and things like that. But yeah, we have another talk about the deep learning aspects tomorrow. So back to rendering. So what we built in this demo and with Halcyon was essentially a hybrid rendering pipeline. There are ways of using ray tracing for everything, and we do that in our reference mode where we path trace. And there are benefits of using ray tracing for everything except when it comes to performance. So what we built actually was a fairly pragmatic hybrid rendering pipeline, and something we want to explore. How do different techniques fit into an overall pipeline that can deliver these type of visuals that we're after? So we start with traditional deferred shading, which we rasterize. We rasterize the G buffer and render it out. It's pretty fast and pretty simple stuff. GPUs have been optimized for this for a long time. Once we have that with the G buffer and the Z buffer, we're able to calculate shadows we primarily just have the sunlight in this scene. And that we can either do through a classical rasterization technique like cascaded shadow maps, or we can ray trace them. And in this demo, we ray trace our shadows. So we pretty much have perfect shadows everywhere in the scene, which is really attractive and requires less tweaking by programmers or artists in that sense, and just works. And we also compute lighting for the sun and potentially other light sources. That's pretty simple. We do it through just any type of compute path, so you can do it through tile-based or cluster techniques, but it's a deferred method that we use here. So that's just using compute. We also do reflections. This is a big complex part. In this scene, we could have done planar reflections and could have some cube maps or some artist manually placed environment maps here and there in the scene. We did have SSR for a while also, but we choose to just go full-on ray tracing in the scenes for all the reflections. And to sort of fill in the light, and instead of having a single ambient term or something like that, we have a dynamic illumination system that uses caches irradiance and calculates that using ray tracing as well, which is something that's very, very difficult to do through just rasterization, and not very efficient to do through rasterization either. Another technique that we use is just ambient occlusion. So the illumination is fairly large scale and not that detailed. Ambient occlusion helps to sort of fill in the decreases in the scenes and add some extra detail and sort of contact shadows in that. That we support both doing through screen space techniques using some fairly high quality screen space ambient occlusion, but we also have a ray tracing mode for it that does it more correctly and more accurately, but at the performance cost. And for transparencies in this scene, we don't have that many, but we use a very different technique there. We actually do it, we do that all through ray tracing and texture space that Colin will be talking a little bit more about later. And then finally, to sort of compose together the entire scene, we do all our post-processing in compute in a couple of different type of passes. There are the traditional sort of bokeh depth of field and motion blur and tone mapping and all that. So we end up with this fairly hybrid pipeline of how everything connects, but that's exactly what we wanted to explore and see what's the right solution for this specific demo for your shadows or for your reflections and translucency. And we believe that this is not necessarily the final answer, neither for this demo. As hardware evolves and as our thinking and the community's contributions sort of evolve and learning evolve in this area, we'll probably change things around here, but we wanted to start to explore it. And we will attempt to do a live demo of this now.
Hello. Okay, cool. All right. So for those of you who were at the Microsoft session, the next 6 slides are a bit of a repeat, but it's only for a moment. I just want to make sure some of the basic concepts from the API are kind of common knowledge for now. And there's going to be additional juicy details that will follow. And so at a high level, this is how this demo is set up with the new DXR concepts. So first, before we spawn a mesh, we build the bottom acceleration for it. So the API allows you to specify multiple types of geometry, but for the demo, we mainly use triangles. And so once the bottom accelerations are built, mesh instances are then specified in the top acceleration. They basically represent a mesh at a specific position and orientation in the world. And then, once a mesh moves, we update its instance matrix, and that's in the top acceleration. We do this for all the meshes, for all the little guys you saw in the video that move around. We do this every frame. It's really fast. I mean, it's just pushing new matrices. So you're not rebuilding ABBs unlike in the bottom acceleration. And then, let me just move down. Okay. And so once all of this is done, well, we can spawn some rays. And we do this, obviously, with ray generation shaders. And we have many of them to support all of our techniques. We have per instance hit shaders for all the ray types, like primary visibility or shadows, or other stuff like that. We have global mist shaders. And all of these shaders need to be accessible at all times for all the rays being launched in the scene. So that's why they live in the shader table. And so first, let's look at how we handled reflections with ray tracing. So like Johan said, we took a hybrid approach where we first rasterized primary visibility. And then we launched rays from the G-buffer. And all of this is done in half resolution on 2x2 blocks, but obviously you can do this in full screen, in full res if you want. We then do a spatial temporal reconstruction at full resolution. And so from the image to the right, you can see how Raytraced Reflections really adds and just works on all types of surfaces, whether it's flat or curved. And our original approach, we tried combining it with SSR for performance, but in the end, we just ray traced just simply for simplicity and uniformity. And so here's a breakdown of how we launch reflection arrays with some HLSL pseudocode to the right. So don't copy-paste this. It doesn't compile. But I just wanted to mark this down in a simple way so you guys get it after if you want to check the slides. And so first, we select one of the 2x2 pixels to trace. We reconstruct the position and vectors from the G-buffer, like the direction, the normals, all that stuff. We initialize our low discrepancy Monte Carlo Halton sequence and a random sequence, a random number sequence that we're going to use to rotate the Halton sequence. We initialize a brand new payload. We prepare a new ray. And when you prepare a ray, you specify the origin of the ray and the direction. And in our case, we actually, the direction is set from the material. So I'll get back to it. So it's not just like so we specify it from the material. We trace, and then we gather the results from the payload. And for temporal filtering, we don't just gather reflection color, but also ray direction, the length of the ray, and 1 over the PDF. And so once we've generated the half-resolution images with the hit results, we reuse them to synthesize the full-resolution output. And so for every pixel in the full-resolution output image, we use 16 samples from the half-res data. Neighbors of high-res pixels obviously provide useful information, but we need to make sure that it's not obvious that we reuse retraced results in the block. So we use a blue noise. We use blue noise to kind of break it up and make sure that in a 2x2 quad, all pixels have different results. And so this kind of provides the spatial part of the filter, which we couple with temporal components similar to TA. And finally, we have a second stage, larger variance-driven bilateral filter to clean up the remaining noise, and it really helps with the rougher reflections, which you'll see in the live demo really helps. And so this is what the world would look like if it was fully reflective, so basically the worst-case scenario. And so with ray tracing, when you handle roughness properly, reflections become so much more grounded, and with the occlusion, it looks so much better and looks really nice. And if we zoom on some details in comparison to the left, you have some really basic SSR. I think Tom put this together in like overnight or something. In the middle, you have our ray-traced G-buffer reflections. Obviously, on the ray-traced ones, you can see under the robot, which you can't with SSR because the information is missing. And to the right, you see our path trace reference. And the thing is, if you squint a bit and you squint the path trace nose away, you can kind of see that our approach is really quite convincing. And so here's another example. Everything feels much more grounded when you have no of these sampling artifacts, especially if you look at the paper clip in the middle. Like you can see how the rays just make sense, and our results look really close to path tracing. And so when it comes to materials, so for this project, we put together a material model that where we combine multiple layers into a single unified expressive BRDF. And by unified, I mean that this model works for all lighting and rendering modes. It's also energy conserving, and it handles Fresnel between layers. So this approach has allowed us to rapidly experiment with different looks. But if you were going to use this in a real game production, you probably want to bake down the number of layers that you'd use. And so here are some of the materials you can find in the demo in the video. As you can see, this approach has allowed our artists to represent a variety of isotropic materials, where rough and smooth varies between the different layers. We also support glass and translucency, which I'll go over in a few slides. And you also probably noticed that we only show isotropic materials. So in the future, we're looking at adding anisotropy as well. And so I mentioned multiple layers. So here's how it works when we need to actually sample. So the general idea is that you only launch a single ray for the whole material stack. And so what we do is we stochastically select and sample a layer, and we estimate its visibility versus the other layers. And so this allows us to attenuate the selected layer by the layers that are on top of it. And so the result is then we then temporarily filter it, but we only store a single value, and so for many layers, so we have to be clever about filtering. I mean, that's the gist of it, and the devil's in the details, obviously, and I guess a full talk could be done on this topic alone, so maybe some other time. But with ray tracing, what's really cool is we can actually do proper refractions, and so you can throw more rays, get translucency and subsurface scattering, and in our case, that's what we got instead of that thickness term that we previously had in Frostbite, which was pre-computed offline and didn't really allow for self-occlusion. Another thing that's cool with ray tracing is that we can actually have the light travel and scatter inside the medium for all the lights and take shadows into account, so we get a more convincing translucent result. And it can also be fully dynamic. So for this demo, like Johan said, we did it in texture space, but obviously you can do it in whatever space you want, or screen space, whatever. So here's a breakdown of how we compute translucency. So for every valid position and normal, we flip the normal and push the ray just inside the surface, just for a bit. We then launch rays in a uniform sphere distribution. You can do as many rays as you want per frame. We only do one, and that's fine. Then what you do is you compute lighting at the intersection. And the trick is you sample previous translucency results. And then you gather, and then you can modulate that with your favorite phase function, whether it's Beer-Lambert or Heine-Greenstein or whatever your favorite phase function is. And then you have a new translucent result. We then filter the results as they converge over multiple frames. So the results, you can denoise them if you want, or you can temporarily accumulate them. If you temporarily accumulate, you have to build a heuristic that kind of works for your case. It has to be reactive enough for moving lights and for objects that could potentially occlude each other. And in our case, we have a variance adaptive mean estimator that Tomasz developed, and which I'll talk about in a few slides when I talk about GI. And so I mentioned shadows and translucency, and so with ray tracing, we get this global shadowing term, and therefore globally shadowed translucency. And this phenomenon kind of happens since objects can occlude each other, and I take this into account when we compute the integration. So as you can see from the images, by occluding each other, shadows allow to have more consistent and better translucency, where objects feel like more grounded in the scene. A similar approach can be used for glass, but instead what you can do is you can just warp the ray based on the view origin and direction. We apply refraction based on the good old Snell's law with IOR values for inside and outside the medium, here air and glass. And what's really cool about DXR is that you know if you've gone in and out of a medium by checking triangle phase transitions, so you can flip the IOR sign there. We trace array in the scene, sample lighting, and then we finish by tinting the results, or you can do something more complicated, or chromatic aberration, for example. And so for the theme of the demo, we used this on pens. And in this case, it was a multi-layer material with the ink tube inside. As you can see, we're not handling shadows properly, the shadow that goes through the pen. But until next time. And so what's cool about this technique is that it works for both rough and clear glass. So for clear glass, you don't need any filtering. And for rough glass, well, we kind of open the cone angle. So obviously, you either need more samples or to get rid of the noise, or you can use temporal filtering. The examples here kind of show a very simple material model for glass, but obviously you can do something more complicated. And so when it comes to indirect lighting or global illumination, for this project, we wanted a technique that doesn't require any pre-computation, that doesn't require parameterization, so no UVs, proxies, whatever, that works for both static and dynamic scenes, is adaptive and refines itself on the fly. And so we went for a point-based approach where we have circles in the world where we path trace irradiance and do runtime Monte Carlo integration, like Johan said. And so we basically prioritize circle spawning by the camera position, the orientation, and the depth. And so once a circle is spawned, it gets added to this global pre-allocated array with atomic add. And in this case, in the video you're seeing there, I had to slow it down to around like 1% because otherwise it's just too fast. You wouldn't see the circles appear progressively. And so this is what it looks like on dynamic objects. So once circles get allocated, they get skinned and they stick to them. And so I mentioned that we compute circle irradiance via path tracing. And so when shooting rays per frame, we limit the depth of the path and the number of paths that we launch. And so one thing that might come to mind is like, well, you're limiting the depth of the path. Does that mean you get fewer bounces as well? In fact, we reuse results from previous frame. So at 1, you get radiosity, and at infinity, you get path tracing. And so I also mentioned earlier that we have a variance adaptive mean estimator when we accumulate results and want these changes to be reactive. So the short version is that we estimate a short-term running mean as well as variance, and based on that, we adjust the blending factor for the long-running mean. And so we keep track of long-term bias, and we try to see that if new samples have been consistently above or below the current mean, and try to catch up if that happens. And obviously, you have to apply this to the scene. So we have binning and culling, and we have voxel grid for that. But that's a bit much for this presentation, so maybe some other time. And the last technique I want to cover is screen space filtered shadows. In our case, we accumulate those and filter them in screen space, and we use the mist shader to figure out if we're not in shadow. We support hard and soft shadows by opening the cone angle. And again, with a wider cone angle, well, you get noise, you have to filter it. So we first reproject results, TA style, and accumulate shadows and variance. And then we apply an SVGF-like filter that has been super simplified, where we have a multipass spatial blur, and that is driven by that variance from the temporal accumulation. And so here's some hard ray trace shadows, some soft but kind of noisy ray trace shadows, and this is the filtered version. So let's zoom in the details. And so, yeah, to the left, the hard, the middle, unfiltered, and to the right, the filtered. And you can see that you get this nice contact hardening while you get rid of the noise. And we'll see in the demo how it turns out in real time. And so one question in the room might be, all of this is cool, but how do you guys handle textural OD since there's no concept of shading quad with ray tracing? And as most people here know, like in the modern GPU, this technique, like textural OD, relies on partial derivatives that you get from the shading quad. That's how you choose textural OD based. It's either automatic or manually. but the partial derivatives come from there. And so, again, with ray tracing, you don't have any shading quads. So traditionally, this is handled with ray differentials. But the thing is, computing ray differential requires differentiating all the elements in the equation for virtual offset rays on triangle plane and storing this data in the payload. And obviously, that's not free, especially over time for subsequent rays. And so an alternative is to always sample MIP0 and do more samples, but that leads to aliasing and additional performance costs. And so together with Aaron's team and Thomas Akenen-Möller at the group in Sweden, we developed a textuality technique for real-time ray tracing. Briefly, the heuristic is based on triangle properties, a curvature estimate, distance, and the incident angle. And what's really cool is that we get similar quality to ray differentials, and we only store a single value in the payload for subsequent rays. And we don't have enough time today to cover this, but I expect an upcoming publication on this topic. But yeah, you have to do a heuristic for now. Do you want to do the demo, or do you want to?
We can summarize.
Okay, cool.
First.
Cool.
The demo seems to be working.
Cool.
Okay. Yeah, just to summarize a little bit of the work that we've been doing. So we see, well, this is just the beginning. The APIs just came out, the implementations are very early, but we do feel this is a really important tool for us going forward, and I think for the industry going forward also. And I want to stress the importance also of just having a unified API around it where we can do compute, raster, and ray tracing as well, interacting with memory and multiple GPUs and all that. That makes it significantly easier. We could have done some of this work before with, well, let's say with optics or with our own tracing or something like that, but this makes it so much easier to work with and integrate and move things between different passes and stuff like that without any interop costs. And the biggest learning here, we just presented a couple of different techniques that we have, and we spend most of the time just explaining how they work. It takes a little bit of time, but it's actually a big thing is just of how it's fairly complex of just the trade-offs between various techniques of like, do you want, how much noise can you accept? It depends on your scene. How about ghosting? How much moving stuff do you have? What's the performance you have, the target in there? And yes, many of these things are fairly expensive, but it's really interesting how you can do these trade-offs. And this scene was mostly opaque, but we're looking at more complex scenes going forward also. And I do think we hopefully showed that you can get to super high quality visuals or even cinematic visuals by combining and being fairly pragmatic about that. But there's a lot more stuff for us to explore, and especially when you delve deeper into more sparse rendering and sort of adaptively distribute ray tracing across the frame where it makes the most, well, has the biggest impact essentially. And as I mentioned, we have a couple of other talks. We did one earlier in the Microsoft session that covered a couple of these techniques a little bit more detailed, and that's more an overview around DXR. We have a deep learning talk tomorrow, and Anastasia in our team is doing a talk about the procedure world and how we built that also. It's built in Houdini. We worked with a bunch of people at Microsoft and NVIDIA. It was a super awesome collaboration. And yeah, lots of references to the work. And we're hiring also, surprisingly. So before questions, let's try and see if the live demo works now. There was a bit of a setup incorrectly with the Windows output. Yes, it works. So here we actually have the yellow dudes are, I'm not sure if they're dudes, the yellow toys things. They are running with these neural networks, and they try and run around to repair these machines. So there's nothing really programmed here, except we gave them some rewards for different type of behaviors. Oh yeah, and Colin, if you activate the agent view also in the top there. So you can see this sort of semantic view that we're giving them that we rasterize in. So this is what they see. This is the only information that they have. And sometimes they can look pretty smart, and sometimes they get a bit confused. And the icon above them is sort of what they're thinking. And we're doing that by estimating what the neural network is sort of predicting. If it's predicting success, but it gets disappointment, it gets angry, which is kind of cute. And if we look at some of a little bit closer on some of the rendering stuff. So, no, not there. Okay, then we'll take questions while Colin tries to not set up the build. Oh yeah, Seb, you should come up also in case there are questions. Questions for both talks. Yeah, we're starting up.
Yeah, this is really great stuff. I'm Calvin from Crystal Dynamics. I'm just wondering, for the Raytraced Reflections, are you guys redoing direct lighting and for every single in the hit shader, and then it's like, I guess you're evaluating another light path there somehow, and is that actually efficient?
It's possible, and we have to do it, and yes, it can be expensive. But yeah, we're doing a shadow array in the reflections there also, and if you had lots of light sources, obviously that would be expensive also.
Right.
You could cache maybe lighting in other type of spaces, so that, I didn't mention that in the summary, but one of the things we're looking forward to is figure out what are different types of spaces we can cache information in for different type of techniques. Reflections don't need to be mirror-like necessarily in most of the areas, and actually most of our, some of the things we really like in this scene is when we have this little more subtle reflections, when an object is just nearby it and you get this fairly rough reflection of something and everything just sort of fits in. But yes, you're right, you have to calculate lighting somehow for your reflections also.
Yeah, it's working, so it's crazy.
Yeah.
First and foremost, I'd like to thank you, Johan. Fantastic presentation. I believe about 3 years ago in SIGGRAPH, there was the presentation on problems in real-time rendering. So back then I mentioned LBVHs, BVHs, and drew a bit of laughter in the crowd. So here we are 3 years later, and BVHs and path tracing. What do you think about voxels?
We like voxels also. And I think, for example, you saw the circles where we're caching information. That's good when you have specific clear surfaces where you can put circles on them. But if you have more volumetric phenomena, or you have geometry in the distance, it becomes more of a volumetric thing in that sense. And then voxels is like one of the only pre-filtered geometry representations that we have. So we are interested in exploring that as well for various type of things. And ultimately, you may have particles in this environment or other things, and ray tracing everything, that's more of an accurate technique, but it's extremely slow to do more softer type of phenomena in it. So yeah, we like voxels also, but we haven't really worked with it that much in this specific experiment at least.
And also in terms of dynamic updates, I mean, like recompiling BVHs versus just the hardware rasterizer, the usual.
Yeah, so building a BVH is it's not too expensive in this demo, but we actually don't even know how much geometry we have in the scene, and we don't have any LODs, but it runs pretty well, and if it's not the bottleneck, we'll figure out how many triangles we have in the scene. But that's a big area of research also, and there's in DXR there's two ways of sort of rebuilding the BVH. You can do the loose refit, and that in some of our experiments is it's like 10 times faster, but it's still early days in this, so see what the performance is. And at least this also gives tools for the IHVs, and given these workloads and other workloads from other game developers to take them and see how we're using or misusing their current hardware, and how they can evolve, and what are the actual bottlenecks in this, because it's news for all of us essentially in this type of context, at least full real-time context.
Thanks again.
No problem.
Hi. So I was wondering whether this technology, I haven't actually looked at the API yet in detail, but is it tied to triangles, or can I ray trace something other than like signed distance field or something like that?
So it has a specific path for triangles and how it builds BVH for it, but you can do custom intersections also, where you just define bounding volumes around anything. So if that's around NURBS or whatever type of representation you want to have, you could do that. That's something we wanted to explore here, especially as there's a lot of smooth surfaces, but we just drew triangles at it in this demo. But I think you can actually probably do quite a lot with it, but there will be different performance constraints with that also, but to build a BVH with other type of representations inside it, essentially, instead of just triangles.
Thanks.
Yeah.
Right. There used to be a problem with coherency with the rays, and there was a lot of work done to make, I don't know, ray trace in packets or something. And as far as I saw the pseudocode, it looked like you only add a ray and then you just don't care about it. So is there anything you can do to make it more efficient, in a sense that, let's say, rays that will go through the same part of the structure would not cache pollute each other or something?
Yeah. So at least with DXR, this specific API, it's a fairly high-level API. So that's the hardware vendors' problems, which is good for us to a degree. So I think it's an interesting point because it's a good. We believe it's a good way to start to get rolling in this sense and start getting workloads. But ultimately, we sort of want the more programmable components that we can perhaps use ourselves, either for our own ray tracing or specialized things, or for how do you say it? Well, other types of techniques within compute. There's a lot of useful stuff here that the hardware architects and the software people that work with the hardware guys have to sort of build on top of this to take these workloads. But yes, in the programming model, you don't care about coherency. That's others' problems essentially, and you can see fairly variable performance if your arrays are very incoherent and things like that also.
Maybe last question: do you think KD trees are dead? Or can you use like a custom acceleration structure? Or you have to rely on what the DXR has on an underlying structure.
So the acceleration structures are kind of an opaque blob. So the IHVs are free to do whatever they want, how they want to optimize it. So in the future we might see some really clever papers coming out of how to do this. I mean, there's been papers on how to build ABBs on GPUs and stuff like that, and so we'll see. But it's free to the IHV to do whatever makes sense for their hardware.
And when we've been talking to them, they sort of want that freedom to be able to explore and try different type of techniques or various optimizations and this trade-off between performance and accuracy in that.
Yeah. And by the way, if you want to check out the demo live, it's going to be at the NVIDIA booth for the rest of GDC, so you can check it out there.
Thank you, guys.
Thank you.